Bismillahirrahmanirrahim. Assalamu alaikum, ladies and gentlemen. So, keeping the usuality, I would like to start from the summary of the previous lecture. Nowadays, a very technical discussion we are doing, and if you come to know, I think you have guessed that as we are going through different methods of detection or problems, then there is something of mix-up of the ideas. So I would like to clarify, I am keeping the things very simple. I am avoiding the intensive mathematics, so that my purpose is to give you just the what is the problem, how you can detect it, and if it is present there, what are the remedial measures that you can adopt. So if you remember, in the previous lecture we talked about the autocorrelation. Simply stated, autocorrelation, if any of the two observations of the residual terms are correlated, we say that there is a problem of autocorrelation. Autocorrelation may arise due to number of reasons. We talked about these reasons. I will like to just give some of the example. There is inertia. Inertia means there is a built-in momentum, and many of the variable, particularly the economic variable, they have some, you can say, the systematic trend. For example, if there is recession, many of the variables are showing downward trend. But if there is boom, many of the variables like GDP, taxes, savings, investment, many others are showing upward trends. Due to this reason, the residual term may be correlated with each other. The other reason may be the curve wave phenomena. Curve wave phenomena simply says that if the decision in this period is based on the previous year, and it is a very applicable phenomena in the agriculture, because if nowadays production is the result of the price of the previous year. So then there is always a specification bias every time in multicollinearity, in heteroscedasticity, and now autocorrelation. This bias is there, that if there is model specification bias, it can lead to autocorrelation, and we saw two kinds of this. That was the excluded variable case, and the other was that the wrong functional form of this. So we started that how to detect this. So before detecting, we concentrated on that what are the problems and what are the repercussions, what are the, you can say, the consequences if autocorrelation is present in your data. If it is there, your OL estimates that should be below are no more below at this time, but need not to worry about this. There is a method, that is the generalized least square, that helps you, that you estimate and you come with the below estimates again. Then when we stopped the discussion, we were talking about the detection methods of the autocorrelation. That how we come to know that there is autocorrelation. As usual, the first and the simplest, and you can say the very clear thing, is that we plot the residual against time. So if they are showing a systematic trend, we suspect and we say that there is the problem of autocorrelation, and we go for some of the remedial measure. On the other hand, if there is no autocorrelation, we need not to worry, as our estimates are now below. After this, there was run test. It was now you can say a systematic, or you can say a formal method to detect the autocorrelation, and I gave the procedure of this. We built on this procedure, we devise a formula for measuring the expected value of the runs and the standard error of the run, and on the basis of this we built a confidence interval, and then we saw in our example, I remember there were three systematic trend in the residual term, and we saw that it was not falling in the acceptance region, it was falling in the critical region. So we rejected the null hypothesis, and null hypothesis was that there is no autocorrelation. So indirectly we came to know that there was autocorrelation, and it was exactly a verification of our residual plot that showed that there is a systematic trend of the residual term, and there was autocorrelation. all the things are based on the hypothetical data, as I gave you the reason that if we are using something's data, we will be making much time that I think that will be not a suitable way to teach. What we are going to cover today? In this lecture, we will complete our discussion regarding the autocorrelation. Detection will continue, and from just after this slide, I am going to discuss a method that is widely used in detection of the autocorrelation, and it is a very simple, only a one glimpse of your on the statistics that will be given there. I am not that is a value there like R square, T, F test, etc. I am going to give some name to that value. You will just look at, immediately come to know that whether there is autocorrelation or not. If it is there, go for the remedial measure. If not, be happy and enjoy the life. Then we will talk about, if time permits, and I hope I will give a brief introduction of the last problem of the regression analysis. Last mean that it is last in our context. It doesn't mean that it is the only last problem. There are many other problems, but we have decided to just concentrate on the four major. The first was the multicollinearity, the second was heteroscedasticity. Today we are talking about the autocorrelation, and if we will be surely giving some information or introduction about the specification bias. After this, our discussion will enter in a new regime that will maybe the dummy variable or something else. Detection of autocorrelation after the run test, we are now concentrating on the formal methods. The first is the Durbin-Watson. The first was run test. The second is the Durbin-Watson D statistics. Very important and very simple and very interesting. D means, this is derived from the name of Durbin-Watson. D means D statistics, that for which the formula has been provided by the Durbin-Watson statistics. Looking at this, we will immediately come to know whether there is a presence of autocorrelation or not. A great advantage, definitely, if I am saying that this is a very important, popular and simple method, it should have some special, you can say, the advantage. A great advantage of the D statistic is that it is based on the estimated residual. Nothing assumes itself. It brings into application the already residual that you have estimated by applying the OLS method, ordinary least square method. So it means already the material is there. We have to just process it, and we will come to know whether there is the autocorrelation or not, which are routinely computed in regression analysis. All this, it is based on the estimated residual, and these are, every time when we run the regression, definitely we can immediately get the residual, because I would like to again refresh your memory. This is the UI hat, and it is equal to yi minus how much of it you have the estimated. So you come with the residual, you have now residual, you can apply the D statistics. Due to this advantage, that it is already material is there, ground is set there. As you apply the regression, ground is set, now you have to just apply some of the formula. Due to this, its simplicity and everything available there, this statistics is reported when you run the regression. And in many of the statistical package, I don't remember that there is any statistical package that is not reporting this. Whenever you will run the regression, like R square, adjusted R square, F test, T test, you will come with the Durbin-Watson that will be called D, and its value will be given in your output. So this is a brief introduction of the Durbin-Watson statistics, or you can say the test of detecting the autocorrelation. Assumption. It is based on the sum of the assumption, and need not to worry, mostly the assumption are the same as are of the classical linear regression model. You can guess now that as it is the material from the regression and we are applying the residual, it means the base of the D statistics and the classical linear regression model is the same. So most of the assumptions we will be talking here, they are the similar. The first is the intercept is present in the regression. I need not to say, I will like just its equation, and I will tell you that what is this. So this tells that y is equal to, so t I am using deliberately rather than yi, because the autocorrelation is a now problem of time series data. So I deliberately replaced I with the t, otherwise I can write I, need not to worry this. So yt is equal to beta 1 plus beta 2 xt plus ut. So what is this? This is, now look at this, this is the intercept. So what the D statistics assume, it makes the assumption that the beta 1 is there, so the model is with intercept. You can say that this is the model and this is the beta 1. If this is the y, this is the x, so the model is beta 1. In other words, what I am saying, the regression is not through the origin. It cannot be, you can say, it is not of this kind. Intercept is present. This is the assumption of this. Independent variable are fixed. I will not explain because I have explained in many times. The error term is normally distributed. This is also the assumption that it has the distribution of, this is the normal distribution. The fourth assumption is the model does not include the lag values of the dependent variable. This is something different, and I would like to explain this, that the model can include many of the independent variables, but we are putting one restriction, that the variable may be up to n numbers, but what is our requirement, that there should be not a lagged variable of the dependent variable. So what is this? Look at here, for example, this is, I say that this is yt, this is ct, that is the consumption is beta 1 plus beta 2, you can say yt. Now it is, I am changing something, sometime writing yt here, something there, but at the same time I am explaining that c is consumption here now, and the yt is the income here. And what I say, if I write here that ct minus 1, that the consumption of my consumption of today is also influenced my consumption of the previous day. It is true, it is according to the theory, but what the Durbin-Watson statistics or the test assume, that there could be many independent variable, but only one restriction is that the dependent variable, that is ct here, it should not be appear as an independent variable with the lag value. And there is another assumption, that is no missing values in the data. Data should be continuous. There should not be a single value missing, because if the values are missing, we will be manipulating data, messaging, as we told in the previous discussion. So these are the 5 assumptions on which the Durbin-Watson statistics is, you can say, the based. This is a very interesting, you can see, this is not a sketch, or you can say the structure of some building, but it is a structure of the confidence interval of the Durbin-Watson statistics. Going to this, you can see that going to this, this shape, or you can say the picture, I would like to first tell you the formula. What is the formula? D stands for the Durbin-Watson statistics. It is a statistic. What is this ui hat? You have now the series of ut hat. This is ut hat. You will be getting it, that yt minus yt hat. Now look at this, I has been replaced by t. Minus ut minus 1 hat. Minus ut minus 1, and this is the square of this. If you have both the terms ut minus 1, and what is this? ut minus 1, this is the square of this. If you look at here, you can see that this is the t, it is from 2 to n. This is the degree of, indirectly you can simply say that this is the degree of freedom. All the same values are used here, that are the sample residual. In the numerator, we are also using the sample residual. In the denominator, we are using, so simple, very simple, everything is with you. Just calculate and see that what is this. So there is also the degree of freedom for this. Now there is, before looking this, the diagram, first see that what is our null hypothesis. If you know there is, we just say that there is autocorrelation, but autocorrelation may be of two kinds. What is the first kind? That is the positive autocorrelation, positive, and there may be the negative autocorrelation. So we have to make two assumptions. There are our two null hypotheses. The first is that no positive autocorrelation, and the other is no negative correlation, negative correlation, and we can even combine the I can say that H naught is equal to no autocorrelation. I can change this autocorrelation in the data. So now you have set, keep in mind, we are seeing that our null hypothesis is, we are assuming that there is no autocorrelation. If we will reject this, there will be autocorrelation, and if we do not reject this, there will be no autocorrelation. What indirectly I am meaning? What I am saying? I am saying that this time our interest is that our null hypothesis is not rejected, because if this is rejected, it means there is autocorrelation. But if it is not rejected, or you can say in a very simple way, I can say it is accepted, we will say that there is autocorrelation. Now come to this. This is, or you can say, this is the center of this confidence interval. This is the 2. From to du means the upper limit of this, dl means this is the lower limit. So on the left of 2, there are 2, from 0 to 2, there is some region that is, this is a different kind of interval, that this region is zone of indecision. If your value falls in the, this is the lower limit, this is the upper limit, if the value, the D statistics fall into this, then we can't make the decision that whether there is autocorrelation or no autocorrelation. Then what we will be doing? We will not keep our finger crossed and we will become, we will make hue and cry that what, there is no solution. There are other tests. Go for those tests. In all the, we have studied many of the tests in multicollinearity, heteroscedasticity and autocorrelation. No test is ever applicable. In different circumstances, one has the more candidature and it can show, it can perform well as compared to the other. So similarly, if you come to the right of this 2, there is another region that is called the indecision region. So what is this? Your confidence interval is starting from here to here, so it ranges between 0 to 4. If you look at this extreme, it is 0. If you look at this extreme, it is. So what is this? At this level, 4 minus du, the upper limit, the 4 minus dl, the lower limit. These that I have showed with cross, these are the region where we can't say that whether there is autocorrelation or not. It may be there, it may not be there. If two persons are doing this, one is in this, the result is falling in this indecision range, one may say that there is autocorrelation, the other may argue, both arguments are very strong. Now look at the extreme left, rejection. What is this? Reject H naught, evidence of positive. If we will reject H naught, this one, there will be positive correlation. If your value falls in this category, 0 to the lower limit of the D statistics, we will say that there is positive correlation, and if on this extreme it falls, we will say that there is negative autocorrelation, as we are rejecting the null hypothesis that there is no negative correlation. Now this is a very gray area. Gray area means you can say the paradise for the D statistics, this all area. And in this area, if our D statistics falls, we do not reject. Look at this here, if we do not reject, then we are happy. Most of the time, when we reject the null hypothesis, we become happy that our results are significant. But this test has been framed in such a way that if we fall in this region, you can say this is the acceptance region. Acceptance region, we say that there is no autocorrelation, because this is our null hypothesis is that there is no positive autocorrelation. So when we accept this, we say that there is no autocorrelation. So this was before mechanics, this was the rejection or the acceptance region. As compared to the other confidence interval, it has some third area, rejection, acceptance, and one area that is indecisive, or you can say that is debatable or not. Rule of thumb. What you will be doing when you there will be D statistics reported in your output of E-views, how you will come to know immediately whether you will build the confidence interval? No. I am giving you a very simple rule. What is this? If D is found to be 2, if it is very near to 2, D statistics is very near to 2, for example, if it is D is equal to 2.10, it is very near to D, I will say that there is no autocorrelation. So what we want, we say that our D statistics should be very, very near to 2. It could be 2. And if it is 2, we are much confident that there is no autocorrelation according to this test. One may assume that there is no first order autocorrelation, either positive or negative. अगर आपकी वैल्यू 2 के करीब आ जाए D statistics की, you can assume that there is neither a positive correlation nor a negative correlation. Look at here, you are just wandering here at this area. So what is this? You are away from the positive autocorrelation, you are also away from the negative autocorrelation. The closer D is to 0, without going there, you will have to tell, look at this, the closer D is to 0, if it is here, there is the evidence of positive correlation. So if there is positive correlation, so your D statistics is going very near towards the D that is now 0. So as it is going towards 0, there is the chance that there is a positive autocorrelation. And if the closer D is towards 4, the greater evidence that there is negative serial correlation. Rather, there is a mix-up of ideas. I would like to use this. This is 0, and now you can say this is 4. So the more you are towards, this is 2 now. If your value is in this area, enjoy the life, enjoy your statistics, and tell the people that your data is free of autocorrelation. But if unfortunately it is more converging towards 0, you will be seeing that there is positive correlation, autocorrelation, and if it is going towards the 4, there is the evidence of that there is negative autocorrelation. So the procedure, how we have to proceed it to get the D statistic. D statistics is there. Now we want to explain that how it has been generated, because you may generate it on the Excel. First is simply run the OLS regression and obtain the residual. I think it is now a matter of seconds for you. You will give the data to the E-views, you will go for open as a equation, you will give the command that you have learned in the previous in the E-views lecture, and I hope that I will be giving one or more or two E-views more lecture, then we will be applying these things and we will be explaining that how there is the issue. Compute D from the formula. Formula is simply there. This is, as you will run the regression, you will get the residual. Now using that formula, you will be easily calculating the D statistics. For the given sample size and given number of explanatory variable, find out the critical lower limit and upper limit, U for upper, L for lower. So now I am deliberately avoiding to give you the formulas for the lower limit and the upper limit. What is the reason behind keeping the thing simple? Because there is statistics that will be given in your output, but at the same time you will be asking that if I am not giving the formula for lower limit and the upper limit, then what is the justification for giving the formula for the D statistics? That is the general thing. You should aware of this, but these are now a bit technicalities, and I would like to say you that you should go for some of the recommended books. You should know these formulas. It will help you to be more you have more command authority and execution on this application. Now follow the decision rule. Now what you have calculated three things: D statistics, its lower limit, and its upper limit. Now you can see, and now follow the rule. Rule is simple. If your D is equal to 2, there is no autocorrelation. Equal means very near to 2, but if it is converging towards 0, there is positive autocorrelation, and if it is very near to 4, there is the evidence that there is negative autocorrelation. Detection of correlation, do not think that there are only two methods, that are the run test or the you can say the Durbin-Watson statistics. There are many other autocorrelation detection tests, but I would not like to explain any of those. If you are interested, you should go for the standard book. One common is that Bruce-Godfrey, that's it, the BG test. It is a journal test. It is applicable to many kinds of data. Consult any of the standard book. There are also other tests of detection of autocorrelation. The immediate question that we should pose, that why there are so many tests of autocorrelation. The reason behind it is that the no test is, or you can say, the perfect or the final test. One test may perform well in one situation. For example, Durbin-Watson may be performing well on one data, and in other data it is not performing well. So this is the reason why there are remedial measures. Definite, now you have detected, and unfortunately if you have found that there is the autocorrelation, no need to worry about. Gird up your line, tighten your belt, and can try to deal with this Herculean task, but ultimately you will be winner, because we have very sophisticated and very simple, and you can say the very accurate techniques that can help us in getting rid of this. The first is change the functional form. We will be talking about this. The first is, as you know, that the multicollinearity comes from one of the reason for this, sorry, not the multicollinearity, autocorrelation. One of the reason of this is the specification bias. So change your model, go to the theory, read many of the articles, reputed journal articles, see whether you have framed or postulated or formulated your model according to the theory. So it will help you change the model. If it is removed, then okay. If it is not removed, then go for the generalized least square method, GLS. In heteroscedasticity, there was the WLS, weighted least square method. Here we will be using that if the problem is not solved by just changing the functional form, we will be applying the generalized least square set. There is another good test way, or you can say Newey-West for large sample. I will not be even touching this, but it doesn't mean that this is less important. It is as important as the other, but as I said, that if I go for each and every test, there will be a very long discussion, and there are even books on that are only on these of the test. In some situation, we can continue to use the OLS method. We just to for your information, I will not be explaining that what are those cases then OLS or estimate, because I would like to just apply the first two things. I expect from you that if you spot that there is a problem of autocorrelation in your data, you come with the first of the two things. Before going further, first of all, I would like to differentiate between pure versus model specification autocorrelation. There is two kinds of autocorrelation. One is the pure autocorrelation. That is our concern nowadays, and we will be talking about pure autocorrelation. How it comes? It comes into the data when there is no specification bias. What I am saying, आपका मॉडल ठीक है, अब अगर आपके जो है वो ऑटो कोरिलेशन डाटा में है, that is called the pure autocorrelation. What this means? That the autocorrelation that comes into the data not due to the misspecification bias is called the pure autocorrelation. So why this is called the pure autocorrelation? For example, if there is specification bias, you choose the wrong model. You excluded the important variable. You included some of the unnecessary variable. This is the specification bias. And look at this. In the beginning I said, change the functional form. If it works, it means, if it works and there is no autocorrelation now, it means the autocorrelation was not pure. Pure autocorrelation will remain whether you change the functional form. It has nothing to do with this, because it has come into the data rather than other source, rather than this, the specification bias. So I am supposing some of the thing, how we come to know that there is a pure autocorrelation or not, and if it is there, we will go further. Example, look at this. For example, this was the model. I say that this was the true model. You change this and you see that there is autocorrelation. Change the model. You change the model. What you take the square of the variable. You, rather than the linear, you made it the non-linear. Again, look at there. Your problem is not solved. So what is this? This is pure autocorrelation. आपने अब कई दफा, I only gave only two example here, that I only change one form of the model. You can change many form of the model, and then you can say that still if your D statistics is not converging towards 2, you say that there is now pure autocorrelation, and you will have to take some of the path to get rid of this autocorrelation. And what is this? The two method, that is the general least square, and this is the feasible generally least square method. We will be talking about this one, that is the general least square method. Before going further there, I would like to say you, प्योर ऑटो कोरिलेशन आपकी ये है कि ये किसी और सोर्स से आ जाए, लेकिन मॉडल स्पेसिफिकेशन की वजह से ना आए. पता कैसे चलेगा? You first assume that the model was correct. When the model was correct, you saw on the D statistics and you came to know, no, there is autocorrelation because this value is not near towards 2. So you change once, twice, thrice, and up to many times. And every time D statistics was not showing that there is no autocorrelation. So now you have spotted that there is pure autocorrelation, and you should go for some extraordinary measure, or you can say methodology, and the methodology is the generally least square method. Generally least square method, how you start this generally least square? For simplicity, assume that this is your model, and the model is of this kind. Yt is equal to beta 1 plus beta 2 xt plus ut. For simplicity, what is the simplicity? It is two variable case, and if it is applicable to two variable case, you can apply it to any number of variable. So what is this? Now assume error term follow the scheme. Now the error term, that is the residual term, we suppose that it is following some of the scheme, or you can say the systematic way. So what is this? This is the systematic way. I will be writing it there in the next slide. So this is equal to, there is another term. This is now our UT is by being generated by rho. This is rho, and this is UT minus 1 plus ET. And ET is now the residual term, and this UT is a now combination of two. This is the coefficient of the residual term, that is the lagged value, and this is the error term. And one property of this rho is it is -1 to 1. It ranges between. These are two extreme, perfect correlation, autocorrelation. Either it is negative perfect correlation or positive perfect correlation. So this scheme has been generated. This is also assumed. This is for simplicity, and this is for, you can say that this is we assume. Now what assuming this, and now there are two cases. One, we say that if rho is known, we know that there is autocorrelation, and what is its degree? Its range is -1 to 1. The more it converges towards 1 or -1, there is higher degree of autocorrelation. So we take that, we assume there are two methods. First, we assume that if rho is known, then we will be applying some methodology, and if it is unknown, then we will be also applying some other methodology. Now we assume if the given relationship, that this relation holds at time t, it also holds at time t minus 1. It is, we say here that if this is now come here, this is the relationship between the variable on current time. For example, today. If it holds today, it should hold on the previous day also. So what this means, I am changing this equation, that is yt minus 1. I am taking this relationship to the previous day. Yt is equal to beta 1 plus beta 2. This is x2t, because t is with it. Beta 2 x2 t minus 1, t minus 1 previous period, and plus ut minus 1. So this is now what we have assumed, that if a relationship holds today, it should hold for the previous day. And now I multiplied all this observation. You can say that this is the equation 1. This is, I multiplied this equation 2 by rho, all terms. You can write here multiply equation 2 with rho. So this will become rho yt minus 1 is equal to rho beta 1 plus rho beta 2 xt minus 1 plus rho ut minus 1. This is now our third equation. Now what we say, we subtract this equation from the first equation. So you will be writing subtract 3 from 1. So what is this? If it is very simple now, yt is equal to yt minus this yt minus this rho yt minus 1 is equal to this beta 1 minus rho beta 1. This beta 1 is this one, plus this, I am writing this beta 2 xt minus rho beta 2 xt minus 1, and this is the error term, plus ut minus rho ut minus 1. So I have subtracted it from there. So now what I can say, I can a bit manipulate this. I can further write it that this is yt minus rho yt minus 1 is equal to, I take the beta 1 common here, beta 1 is equal to 1 minus rho. This is just, I have taken the common using the mathematical trick, that this is, I can take the beta 2 common and it becomes xt minus rho xt minus 1, plus I can take that, what I can take the, that is et. I can write it the et and it is ut minus, it will become ut minus rho ut minus 1. As usual, I have written, I have not taken something from here. Now I would like to express this variable by yt star, just generating a new variable y star, and it is yt star. yt star कुछ भी नहीं है, सिर्फ इस सारी वैल्यू के बराबर है. And this is now beta 1 star, and beta 1 star is equal to whole this value. Let me check here. Beta 1 is equal to, look at this, this is whole value, and yt star is, look at this, equal to, and now the other is xt star. So here plus beta 2 star, and beta 2 star is simply equal to beta 2, and it is xt star, and xt star is equal to this one, and plus et, and et is now equal to this one. So I have just replaced, I have done some mathematics and then I have replaced. Now what is this? Now if you apply OLS, now you have made some of the, you can say the mathematical derivation, you can say, apply OLS on the transformed variables. Now transformed variables are yi star, yt star, xt stars. Now we can apply on OLS this, and what will be the estimator will be below. This is GLS. Simply speaking, GLS is nothing something new. What we did, we assumed that there is the row is known. We changed our model in such a way and applied the same OLS. अगर हम इस मॉडल पे OLS लगा दें, look at here. If we apply OLS, beta 1 hat and beta 2 hat will not be below. They will be linear, they will be unbiased, but they will be not biased. They will have not the minimum variance. But look at this, after some transformation, if I applied the same OLS procedure on these transformed variable that are now yt stars and this, and you know yt star is equal to this one, beta 1 star is equal to this one, and you can say the xt star is equal to this one. If I applied the same on this, that will become the GLS, and fortunately our estimates will be now below. So this was one of the techniques of when the row is known. We suppose that row is equal to, we know the row is there, and we assume that this is a known. And this was the GLS. Now when the row is not known. So the second is, when this is not known, apply first difference model. What we will be doing? We will be doing the first difference model, and the first difference model are yt minus 1. Simply, there is nothing. Now we are not multiplying the row here. Now the role of row is outside the picture. Why it is outside the picture? Because it is known there. It is now known. At there it was just coming as a, you can say the parameter as row. Now it is known, and we will see it ranges between -2, 1, and we suppose that it is equal to, row is equal to 1. Now this is known. So previously it was unknown, we were multiplying it by row and we were just giving the manipulating and then reaching the transformed variable. Here what I am saying that it is now known, and now row we are supposing just that it is equal to 1, that there is a perfect autocorrelation. So what this means, go to our previous model, that was that yt is equal to beta 1 plus beta 2 x 2t plus ut. So just the next is that suppose rho is equal to 1, the previous model becomes, if I take its difference, it will becomes yt minus 1, again the same story, beta 1 plus beta 2 x 2 t minus 1 plus ut minus 1. So what this means, I am differentiating these two equations, I am subtracting this 2 from 1. You can see I am a bit quick because I have just completed all this, so I would like to go a bit quickly. So this will again become yt minus 1 plus beta 1 minus beta 1 plus beta 2 x 2t minus beta 2 x 2t minus 1 plus ut minus 1. So what is this? Now rho is equal, it is the same model, look at here, this is the same model, this one, but the difference is that rho is equal to 1. When rho is equal to 1, this will vanish, this will vanish, this will vanish, and this will also vanish. So now rho is equal to 1, it will vanish here. So when it will vanish here, the model simply becomes this one. And now let me show this how it becomes. This will cancel out and this will become, this is now change in yt, this will become delta yt and it equal to beta 2. This is change in xt, that is delta x2t. So what this means, x2t is equal to now x2t minus x2t minus 1. So this is the situation, the model becomes in this way, and plus this is I am showing this, that this the whole term is 80. Now we have transformed the model in the similar way, but one difference is there, that in the previous case the rho was unknown, but here rho is known, and what is known we have supposed that it is equal to 1 and there is a perfect autocorrelation. So the model becomes of this is delta is, this is for change. So what this is, now run the regression. Regression is with us, these are the variable. Now we can run the regression. Look at this, you will be confusing. This is yt, for example 5, 6, 7, 8. What is this yt minus 1? This is from the previous value from here, and this will become yt minus 1 previous value, this will become 6 here, the 7 here, the 8 here, one value, first value will be vanished, and this is yt minus 1. Now you have the values 5 minus this and this and this, so on. So similarly in the case of x. Now one thing is interesting about this model. The model is without the intercept, and you know now that now the regression is running through the origin. I am not saying that why it has come. I am just ringing the, you can say, the warning call that we have got rid of the multicollinearity, but regression is through the origin. No matter that regression is through the origin, but you should know its features, its drawbacks, its benefits, so that you could come with any of the other problem. Now why we take the rho is equal to 1? It is a very highly debatable issue. Like as we said, the alpha, that is the level of significance, there is much more discussion. हमने तो simply एक के बराबर ले लिया और कहा कि जी वाह वाह हो गई, but it is very debatable. Some people say, give different formulas for this, but I am not going to any of the formula because it will become too expanded discussion. So I have just told you that it is a very critical issue. Now this model has two advantages. One disadvantage, that it is the regression running through the origin, but now it has two advantages. What are the advantages? The first advantage is that autocorrelation is corrected. Autocorrelation is corrected. You removed your autocorrelation out of the data and you are now free by transforming in this way. The second one important, that is by chance, and incidentally it was not our purpose to do that, but fortunately it happened that our non-stationary variable, stationary series, or you can say series or variable, are now stationary. What is stationary? Now their mean, their variance and covariance is constant over time. You have now killed two birds with one stone. What happened? You just went for the correction of the autocorrelation, it was solved. And the other was that you, due to this, you also got rid of the problem of non-stationarity. Non-stationarity is also a very critical and crucial issue that leads towards the spurious regression. I am not interested to just give you any of the detail here, but I have just told you that this is very important if the row is known, and most of the time it is we have its value, and if it is unknown we are manipulating in other way. If it is known, we are manipulating in some another way. So our discussions completes about the autocorrelation. I am not going to give you a summary, but I will just give you one hint of the next problem, and then I will go back for the summary. So what is our last problem of the regression analysis? Keep in mind, regression analysis have more than 4 problems. Now help me to count. The first was the multicollinearity. The other was, I think you are guessing, the heteroscedasticity. The third was autocorrelation that we have just completed. And now there is the problem of model specification. If you remember, now what we are doing, we are lapsing 1, 2 and 3 or any of the assumption of the classical linear regression model. One warning is there that when we lapse one of the assumption, the other assumption are maintained in the same way. For example, in the heteroscedasticity, when we said that there is non-constant variance of the residual term, all other 9 assumptions were maintained. So need not to say when we are lapsing one, or you can say we are allowing one of the assumption to be relaxed, the other assumptions are at the same time maintained. So classical linear regression model assume that the model is correctly specified. This is the one fundamental and basic, that we assume that our model is correctly specified, because if we are unable to take this assumption, we cannot go even one step further. What are the criteria? If two people come to me, they show that whose model is, you can say, without bias, so I should set some criteria. So what we are going to discuss in this, I am going to tell you that what is the criteria in choosing a model or for empirical analysis. There are many models that will be competing with each other, and you will have to choose from those models. So what is the criteria? In the previously we saw some criteria, that was the R square. You know, that was that how much proportion is being explained of the dependent variable but independent. Now we are going further, you can say concrete, and we will tell that what is the problem. After this, what we will discuss, what types of model specification errors, किस तरह के blunder आप जो है आप, I am also with one of you, we can make blunder in this mistakes, blunders of this, and we will have to know that what kinds of these things, which kind of you can say error we can make. What are the consequences of specification error? क्या इसका कोई इशू भी है या हम ऐसे ही शोर मचाए जा रहे हैं that there is a problem? For example, if a person or student comes to me with the linear model, the other comes with the non-linear model. If there is no difference of model specification, then why need to worry about this? Just let the things, shut your eyes and see that this is by intuition and you have done this. Now, after this, we will discuss that how does one detect specification errors. That if there is error, then how we are able to detect this, and when it is there. I always assume that no problem is there. I wish good for you, wish best luck for you, that I say that every time when you test, you come with that there is no problem. Because I think you are afraid of this, that how you will get rid of this, but it is only if I say that every time you are not confront with the, you can say, the problem, I am living in full paradise. Because the problem of there in reality, if your data is from real life, it has many problems: multicollinearity, autocorrelation, heteroscedasticity, and at the top there may be the specification bias, because I can say you didn't go through the intensively into the literature and you just came on the first model you saw in the paper, and it was not matching according to your phenomenon. And what are the, how we, when there are competing model, how we look at their efficiency, that how they are. So I would like to start from that model specification. What is the criteria for this? So what is the criteria? Is the first is be data admissible. Our model should be data admissible. What this means, that the prediction made from the model must be logically possible. Only we should not make the, you can say, the castle in the air. हवा में तीर नहीं चलाने. Our model should give a reasonable, justifiable, measurable and smart logic of prediction. For example, if my model says that if we increase our GDP by 1%, our savings will increase by 2000%. It is ridiculous. It is something beyond the limits of our data. So first criteria is when there is, you can say, then there are the predictions. The prediction based on your model should be logically and defendable, and it should be, you can say, the logically possible. ऐसे नहीं है कि हम कह दें कि only if we spend 1 unit into education. For example, if I say that if we increase, if our education expenditure to GDP ratio is now around about 2. If I say to any of the, you can say, the political leader, for example Imran Khan and Nawaz Sharif or Zardari, that if we increase it by 1%, we say that now it is 3 GDP, all the Pakistani will become literate. It is not justifiable because it is a very minor amount and there is a huge number of people that are still illiterate. So the first criteria is the data is admissible. Be consistent with the theory. All your model results should be according to the theory. I would like to give the example from the quantity, demand and price, that whatever the situation, there should be negative relationship. Because as the price increases, people reduce their quantity, demand, or you can say the purchasing. If there is a positive relationship, it is not defendable. It is only defendable when there is some special kind of circumstances. It is not from the real data. We can say that you collected data. I am not objecting that you manipulated the data by writing on your in your room, but I can say that the data has come from some of the abnormal situation. So in most of the time we are dealing with the normality. So it should be consistent with the theory. Have the third thing, the criteria is have weakly exogenous regressor. What this means? It is the assumption of the classical regression model that the regressor must be uncorrelated with the error term. They should not be correlated with the error term. If they are correlated with the error term, you know what are the consequences. It is simply that, just to remind you, expected value of xi ui is equal to 0. Exhibit a parameter consistency. The parameter should be consistent. It doesn't mean that they are fluctuating, or you can say they are not consistent over time. They should be consistent. Every time your prediction should be in the same region. The fourth is the exhibit data coherency. The residual estimated from the model must be purely random. For example, if you apply the, let me see, there is space. So what is this saying? That if you plot the residual, these should be of this kind, showing no trend. These are, you can say, the UT residual, and this is the time. These should be, this should be showing that the data is coherent. This means that the residual are random. And the last is be encompassing, that all the good, you can say, the characteristic of all the model should include in your model. For example, if you choose a model, all the good properties of B, C, D and E model should be included in this model. Indirectly, what I am saying that your model should not be improved. This should be the most improved form of this. So this were some of the, you can say, that the criteria that we set to choose that the model is correct, or you can say the model is logical, or the other things. So I rather than going further, that this, what are the specification bias, I would like to just close the here, and I would like to give you a brief summary of the previous 1 hour. In the previous 1 hour, we started from the detection of the autocorrelation, and we started from the Durbin-Watson statistic. Very simple, very you can say interesting and widely used, and very easy, because most of the time D statistics is given in your output. What is the D statistic? It can be estimated from the sample information, and you are using only one term, that is the residual sum. Sometimes residual sum of square, sometimes their legs, and you know the formula for this. So what is this? What is the rule of thumb? If your D statistic is very near to 2, you can say that there is no autocorrelation. But as it will converge away from the 2 and converge towards 0, there will be positive autocorrelation, and as it will be converging away from the 2, it will be leaving 2 and converging towards 4, there will be negative autocorrelation. So the ultimate solution is that as D is very near to 2, there is a rule of thumb that we say that there is no autocorrelation. Be careful that there are two regions on the both side of 2 that are indecisive. If that is the situation, go for some of the other tests. The other thing we detected after Durbin-Watson statistic, we just completed 2 tests. That was the Durbin-Watson, and in the previous lecture the other was, you can say, another method for detecting the autocorrelation. After this, we said that how to get rid of this. There was the generalized square method, and it can be applied in 2 ways. First, the rho. Rho is simply, you can say, if I speak in a very simple way, I can say that this is the coefficient that is attached with the error term, or you can say it is the measure of the degree of the autocorrelation, because autocorrelation is the correlation between any of the 2 residual terms. So if it is known, we apply the generalized least square on the transformed variable, and if this is, you can say, if it is known, if it is, first we applied known, it is known, and then we said if it is unknown, or I may be some bit, you say I may be forgetting something. Let me go for this to clarify. First was that if it is known, and the other was it is non-known. So if it is known, we transform the variables and apply the simple OLS, and our parameter becomes below. In the other, when it is not known, we suppose it is equal to 1 or something else, and we do the procedure. Only two benefit, one disadvantage. Benefit is the disadvantage is that the regression is through the origin. The benefit is that you kill two birds with one stone. You remove the autocorrelation, and the other is you make your non-stationary series stationary. Then we just started the introduction of the fourth, last but not the least problem of the regression analysis, and that was the specification bias. Specification bias, the model is not correctly specified, it is misspecified. We will set the criteria that how we will come to know that whether the model is correctly specified or not. We talked about 4 or 5 things, that it should be according to the data admissible, it should be data coherence, and you can say the parameter should be consistent. So keep touch with the books, your notes, this my lecture, and try to get command more and more on this. From the next lecture we will be just talking about the specification bias, and then we will be going towards some other topics that may be the dummy variable and the other. They are all on based this lecture. So till the next lecture, take care, goodbye, and Allah Hafiz.